My name is José Antonio Contreras. I'm a PhD student from the Engineering Institute of the UNAM in Mexico, and I'm very glad to stay here at this Congress. Today, I'm going to talk about the denitrifying anaerobic methane oxidation high-performance operation in a continuous bioreactor. So, to begin with this presentation, why is it important to study this topic? Well, that's because in recent years, the anaerobic digestion has been widely spread into the world, especially in Europe, the United States, and China, which are the top leaders in terms of biogas production. The anaerobic digestion has become very popular because it offers a sustainable way to manage organic wastes and also to produce a biogas with energetic qualities at the same time. However, liquid streams from anaerobic digesters have been identified as critical greenhouse gas hotspots. And to get a better perspective on this, we need to look closer at the anaerobic digestion. During the anaerobic digestion, organic materials are transformed into methane, the main component of the biogas, and carbon dioxide. This biogas can be upgraded and then used to produce electrical and thermal energy. However, important amounts of methane remain dissolved here in the liquid fractions of the digestate by the chemical equilibrium. So when these liquid streams are purged and stored under environmental conditions, the dissolved methane is released into the atmosphere, representing a serious pollution problem because it has been estimated that every cubic meter of digestate can release up to 18 liters of methane into the atmosphere. Moreover, during the storage of these liquid streams, more methane can be still produced, increasing the amount of these emissions into the atmosphere. Considering that methane is a strong greenhouse gas with a global warming potential 30 times higher than carbon dioxide, it's necessary to develop cost-effective and environmental friendly technologies to deal with this problem. The anaerobic oxidation of methane coupled to denitrification, also known as N-AOM, is a promising biotechnology, which main objective is oxidize the dissolved methane until carbon dioxide. And to perform this process, we can take advantage of two commonly pollutants found in the wastewater treatment plants and other biogas producing facilities, such as the nitrate and the nitrite, preventing other environmental problems, such as the eutrophisation. However, most of the N-AOM studies performed until now, most of the N-AOM studies reported until now in the literature have been performed in non-continuous systems, and the few works in continuous have employed hydraulic retention times in the order of months or weeks that in many cases are not suitable for the real application of the process. Moreover, nitrate has been by far the most common electron acceptor study, and the effect of the nitrate, which is more favorable from the point of view of the thermodynamics, is still unclear. So considering these limitations, we decided to perform this study where the general objective was to evaluate the performance of a continuous N-AOM reactor operated at a short hydraulic retention time and supplying nitrate alone and in a mixture with nitrate as electron acceptors. To achieve this goal, we decided to build up the system that you can see here in this picture. Basically, the gray lines represent electronic instruments, the blue lines gas flows, and the red lines liquid streams. Here, we fed a mineral salt medium enriched with nitrate alone or in mixture with nitrate, and this liquid was fed into a column where we supply nitrogen to deoxygenate the liquid. Then the liquid was fed into the reactor where the process took place. The bioreactor was operated maintaining an hydraulic retention time of 17 hours. And one of the things that characterized this work is that dissolved oxygen was measured in the reactor and in the column to guarantee that an anoxic process was performed here. And it's basically one of the big differences with respect to other works, because in many other works, dissolved oxygen is not measured, so there is no warranty that other alternative metabolisms may occur. And finally, we install a settler to recycle the biomass all inside the process. The experimental operation was divided into two big stages. In the first one, we only supply nitrate as the unique electron acceptor, and in the second one, we supply a mixture of nitrate and nitrite, maintaining a ratio 1:1. During the first stage, we observed, or we were able to achieve, methane elimination capacities around 30 grams per cubic meter per hour, which are represented here with the red points. But in the second stage, elimination capacities above 50 grams per cubic meter per hour were reached, which are the highest reported so far in the literature. In addition, carbon dioxide production followed a similar trend than the methane elimination. And indeed, if we obtain the ratio between the carbon dioxide produced and the methane elimination, we will see that this ratio is very close to the stoichiometric value expected of 2.75, indicated that the N-AOM process was carried out. With respect to the nitrogen removal, we also observed significant differences between the two stages. For instance, in the first stage, we obtained an average total nitrogen removal rate around 30 grams per cubic meter per hour, but in the second stage, nitrogen removal rates around 20 grams per cubic meter per hour were reached, which are very similar to other specialized denitrifying processes such as anamox. And in this case, we also measure another key parameter, which was the nitrous oxide emission factor, which basically indicates what percentage of the nitrogen removed was used for the microorganisms to produce this compound. And this is very important because nitrous oxide is also a greenhouse gas, and its production and accumulation is not desirable in this kind of processes. But fortunately, the percentage of the nitrogen that was transformed into this compound was always below 1% during all the experimentation. So what is the contribution of this work? Well, the first one is that we were able to implement the N-AOM process in a completely continuous system and operating under a short hydraulic retention time. We also observed that methane oxidation was higher when we supply a mixture of nitrate and nitrite compared when we only supply nitrate alone as unique electron acceptor. The maximum methane and nitrogen removal rates achieved in this work are higher than those reported in the literature, so this represents a step toward the real application of the process. Most of the results that I have presented you today have been recently published in the Chemical Engineering Journal. So I would like to invite you to check out more information in this paper, because we also perform another specialized analysis related with changes about the microbial communities and the enzymes expressed along the experimentation. So if you are interested to get more information, you can check out this paper. And finally, I would like to thank the economical support from these Mexican institutions, and also I would like to especially thank you to my research group, because without their help, this work wouldn't be possible. So that's all of my part. I appreciate your attention, and thank you very much.